So my name is Sami. I'm the technical program manager at Facebook. Today with me is Leung, who is also a mechanical engineer at Facebook. And here today we are here to talk about MiniPack. It's mechanical and thermal cooling design. So it's a brief introduction of MiniPack hardware architecture. So what is MiniPack? So MiniPack is Facebook next generation 100 gig switch. It's based on cutting edge technology, switch technology based on Broadcom Tomahawk 3 switch chip. It supports mature optics, 100 gig CWDM light, and compared to its prior generation switch, which was backpack, it occupies about half of the space and consumes almost half of the power. So most precisely compared to backpack, which was an 8U switch, it occupies 4 RU. It consumes close to 1400 watt compared to about 2600 watt power, budgeted power for backpack. And has a radix of 128 port. So a little bit about the history of the platform. MiniPack was announced in OCP Global Summit earlier this year in the month of March. And it was formally accepted by OCP committee as a accepted design in the month of June 2019. So some of the important components of MiniPack architecture. So if you look at the MiniPack architectures, basically it has SMB board, which is the switch main board, which hosts the switching chip, BMC, and associative circuitry. Also, a very important component is the SCM or system controller board, which hosts the system CPU along with its associated memory and circuitry. And this module is field replaceable or FRU in the field. Also in the system is a port interface modules or PIM as we call it. These are the interface card which provide connectivity with outside the switch. So currently with the MiniPack chassis, we introduce one type of PIM, which is PIM 16Q. PIM 16Q has 1600 gig port with each port QSFP28. Okay. Also in the systems of fan control module or fan controller boards, there is one on the top and one is on the bottom. The power distribution system consists of two components. One is the horizontal bus bar, which distributes the power to the whole system. And in order to control the flow of power, there are two power controller board or power controller systems, one on the left and one on the right. Also very important part of the design is DOM FPG or digital optical monitoring FPGA is part of the PIM card. And the main function of this FPGA is to facilitate moving the data in and out of the optical module. So here's a brief overview of the chassis architecture. So you can see the chassis architecture is based on orthogonal direct design or architecture. There is no backplane, which facilitates the open airflow through the chassis. That improves the thermal efficiency of the cooling system. It supports 100 gig optics light and cool it down up till 55 degrees centigrade. Because of the orthogonal architecture, it facilitates short route lengths of the trace. That means lower insertion loss. In terms of the PIM card, even though we are introducing one type of PIM card with the chassis, which is a PIM 16Q, but any user, they can take the chassis and can design future PIM cards which fits their application. And then lastly, the most important part is the fruable SCM or system control module, which hosts or facilitates COMI mini-lake board, which is the system control module. And you can see on the picture, the PIM cards are at the front. We have fan at the rear, and then we have cooling system from a Tomahawk 3 in the center. So a little bit about usage of MiniPack. So in fabric architecture, we have multiple level of usage at Facebook, and we have successfully used this box for fabric switch as a spine switch and a fabric aggregator application. and has been tested, has been used with the multiple generation of rack switches. So is a brief introduction of the mechanical spec of the chassis. The dimension of chassis are 176 by 440 by 738 millimeter. It weighs almost 54 kilogram. It has 8 fan assemblies, 8 PIM cards, like I said, 1 SCM, and has 4 1500 watt power supplies. It has handle and handle pocket, one on the left and one on the right, to facilitate the installation of the chassis. So at this time we'll have Jimmy Leung come forward and take a deeper dive in the mechanical and the thermal design.
Good morning. My name is Jimmy Leung. I'm the mechanical architecture for MiniPack. So as you can see, Sami already mentioned, MiniPack utilizing orthogonal design direct made connectors to do the architecture design. So it allows all the PIM card and SCM card connected orthogonally with the SMB board in the system. And also it utilizes the segregated data control and management plane design for the system itself. Yes. So this is a top cross-sectional view to show the inside of the MiniPack. As Sami mentioned before, we have the SCM, System Control Module, which contains the MiniLake design. It's a custom COM-E design for Facebook. And then we have the 8 PIM card on the front of the chassis. And then we have utilizing a Tomahawk 3, the Broadcom Tomahawk 3 ASICs. And if you see underneath this big radiator, that's the switch ASIC where the Tomahawk 3 resides. And we're utilizing in this design, we have the thermal siphon for the cooling applications. And we have 4 PSU, 2 on each side of the rear of the chassis, and also 8 fan tray on the rear side for the cooling. Next. This is another cross-sectional view to show how's the PIM card oriented. So yeah, as you can see, the PIM card is vertically oriented, and the SMB board is horizontal. That's how we can utilize the direct made orthogonal design in this architecture. Right? So this is basically showing all the throughs from the front of the units. So the first one on the far left, this is the SCM module, and then the rest of the 8 modules is the PM16Q. Right. Next. And on the rear side, all the throughs are 2 PSU on each side of the rear of the chassis, and 4 fan tray in the rear for cooling. So why we use BMO? Mainly is to allow the cooling for the system to be the most effective way. Once we remove all the through from the front and the back of the chassis, you can literally see through the entire chassis from front to back. It's pretty much just a frame. And all the conductor on the bottom, this is the SMB where it's located, and that's all the connections to the switch main board from the PIM card. Next one. So we don't have a back plane. So we still need to have some structure on the chassis. What we did is we utilized a machine part to do the frame to support the middle of the chassis, where's the key of the system, to also do a lot of major alignment between the system main board and the PIM module and SCM. And also this allowed the most open airflow path that we can have for the system cooling. So we utilize this aggregated architecture. So we have all the SCM PIM card. Major cards are made orthogonally, like I mentioned before. So we also separate up the channel between the system and the PSU. We have a picture to show it later. With this orthogonal design, we reduced the PCB trace length, so it improved the SI performance between the PIM card and the assembly board. And because of the cooling, it allows us to cool the optics using a 55C, low-cost 55C CWDM for optics in the system. All right. So these are the major components. As we mentioned, SCM, PIM, fan control modules. We have two fan control modules, one on top and one on the bottom, on the rear side of the chassis. And each fan control modules house 4 fan tray assembly. And then also we have a power distribution system, which contains a bus bar, horizontal bus bar, a left PDB, and also a right PDB. Power distribution board, that's what it is. So this is a fully loaded view of a MiniPack with 8 PIM 16Q showing. They are all 128 ports total, 100 gigs port, yeah, 128 of them. Next, okay, on the front, as I mentioned before, we have a left PSU channel and also a right PSU channel. We purposely separate them because we don't want the system cooling and the PSU cooling fighting each other. So we designed it to separate it so each of them can control their own cooling in the system. And on the front we have USB jack for technicians. When they service the units, they can ground themselves to the unit without accidentally shorting the units. And then we have a pull tab to show where the system information is on the system. So they don't need to run around to try to figure out where it is. So back. So on the rear side, you can see 2 PSU on each of the side of the chassis. The way we number the throughs is, if you're looking at the chassis from the front, it's always from the left and also from the top. So on this view, imagine you're standing on the front. So PSU 1 is on the top right if you're standing in front of the chassis. So that's how we number all of them to be a lot consistent in our data center. So the technician doesn't need to guess. They always think this is how we number all. And when they service it, it's much easier. And similar back, on the back, they have ESC jack and also ground lock mounting for grounding the chassis, the safety ground for the system. And then we also have, because we have rail kit design, so we have some hold down on the rear of the chassis to support the rear side. So it doesn't bounce if there's any earthquake or anything going on in the data center. Next. So power distribution system. This is how this power distribution all assembled together. If you look carefully, in the middle, it is a 2-layer bus bar design. And then the PDB is on the right-hand side and on the back, on the left-hand side. There's a mechanical sheet metal bracket to hold this assembly together, so they can easily drop in when we do the assembly of the chassis. Next. Okay, so we flip the distribution system to show basically is how we connected from the PSU to the PIM card, how the power is being distributed. So the PDB connected to the 4 PSU on the rear side of the system. And then we're utilizing the busbar braided connection, which is 2 copper braided cable, or 2 on each side, ground and power, to connect it to the busbar, different layers. And then it connected through the cool power connectors, and it will distribute the power to the each of the front through modules. So this is another view showing how this assembly all works together. Next slide. So mention cool power. Since we're utilizing a DMO type connections, so we kind of like drive us to also design the power connections to be orthogonal also. That allow us to a little bit more freedom to connect it the way that oriented in the system. So for the fruits, same, you already noticed by now that's how many fruits that we have. Is the SCM board, PIM, fan tray assembly, and also the PSUs. And then on the SCM modules, we use the MiniPack, which is a custom-made COM-E modules that for the system control. And we have used the SATA M.2 SSD in these SCM modules. So this is the view showing how the SCM card looks like. And next. And this shows the major components on the SCM modules. So as you can see, the COM-E is this big piece in the middle rear, and then there's a SATA M.2 right there, and we have some OB5 and SFP connectors for the connections up in the front. Thanks. And for the PIM card, right now we have a PM16Q. As Sami mentioned before, other company, if they decide to use this system, they are very flexible. You can design another PIM card to work with the system. So it's not limited to only the QSFP interface. Same thing, we're using same DMO connectors and also the cool powers to support this PIM card. And this is how the PIM cards looks like. And the PIM card, because it's a DMO connections, we also utilize the Broadcom Gearbox, the 81724, to make sure the signal is maintaining. And this is how the rear of the PIN card looks like. And we're utilizing the Amphenol XMX connector for our DMO design. For the fan tray assembly, the fan tray assembly is a toolless design, which is we don't use screw to latch the fan tray. It will save a lot of time in our data center if they need to replace any fan. We're utilizing a 80 by 80 millimeters counter-rotating fan, so it provides the high pressure and also enough sufficient airflow. It's hot swappable, and we have a LED indicator on the back to indicate if there's a failure on the fan tray assembly. And we mentioned there's 2 FCM modules in the system. So we have each FCM module house 4 of the fan tray assembly. And we're utilizing a high efficiency PSU, power supply unit. We use the HVAC connectors, and also because of the high efficiency, we utilize that connectors, and also it has a built-in latching mechanism. So in your data center, you don't need to spend extra effort to find a way to tie your power cord to support the power cord, so you don't accidentally unplug. So on the thermal design, this is a front to rear airflow cooling, as you can see. For the fan, it's N+1 redundancy. And also because of that, we can cool the 100 gig modules, use 3.5 watts each maximum at a 55 C case temperature of those optical modules. It allows up to 35 C ambient and 6,000 feet altitude. And also, worst case is like under 1 fan rotor failure. And then like as mentioned before, the PSU has its own channel, so your system doesn't fight with your PSU cooling, so they have their own airspace. They can cool how they want to cool it.
Is that front to back airflow as well for PSU?
Correct. And each PSU has its own fan inside. So if you look at it like the system versus the PSU fan, the system fan actually has much higher power compared to the PSU. So you don't want that to have a recirculations. So that's why we separate out the air channels. And also the system delta T depends on how your data center will set up. So you can adjust the threshold to control that delta T. And for MiniPack, we already approved by the OCP, and all the design file is available in OCP community. So please, download if you want to check out the design and share your experience on to the community on the MiniPack. Here's the information for the MiniPack design files. All right. Any questions? Yes.
So I read it supports about 3.5 watts on the optic sides for
Yeah.
100 gig. You guys are using
CWDM.
Light.
What if you want to use a limited number of PAM4 optics that are a little bit higher in their power requirements? Do you have any experience with it at all? Like, for example, Microsoft is heavily using those.
Mm-hmm.
A lot of switches support a limited number of them, because if you fully populate it, then obviously the whole thermal design needs to change. Or have you not considered that?
I think when we do the thermal design, we're utilizing the 3.5 watts for every single port. So you can populate all 128 with 3.5 watts optics.
Okay, so if some of the ports use less, there's the flexibility to use some ports with more.
Oh, you mean some that go beyond 3.5?
Yeah, the PAM4 is about 5.
So only on okay, if you look at the PIM, they're all vertical, right? So there's 2 rows vertically. Only the left row, if you want to use the higher power one, because we're utilizing a stack cage design. So the right row is basically kind of sandwiched between one of the QSFP and the PCB. So it's more thermal effective to use the left-hand side if you want to use a higher power.
Sorry?
What power?
So I think the PAM4 is around 5 watts.
PAM4?
Yeah, the
You're
PAM4
talking
is
about
about
regular MSA, right?
What's the MSA case temperature specification for that?
Yeah.
Oh, that's a bit.
Because we did this for 3.5 watt CWDM for light, but we try to keep it under 55 degrees. If
Right.
By the standard, it's usually 70 degrees, right?
Right.
Yeah, I think 5 watts and 70 degrees, if you use the left ports, should be possible.
Yeah. And also one thing is when we design the system, because our data center has their power limit per rack, so we want to design it in a way that's very specific, very thermally very efficient. We don't want to drive the fan power high, so that's how we can keep the efficiency of the thermal very efficient. Otherwise, if we start putting much higher optics in there, we'll have to drive the fan speed higher, which would draw much power, right? I mean, for us, the system is capable of doing that, but for our application, we want to keep it in the more efficient way to do it. Yes?
So that says that this is 100G based only. Because if you were going to go into a higher data rate, you'd have more power consumption.
Correct.
But you could also have a different pin design,
Yeah.
right?
Because it's all modular design, so you can design a separate PIM with higher power modules. Then you can utilize this system.
But you have to change the airflow as well.
No, because it's adjustable fan speed control, so you can using BMC to adjust the fan tray, the fan duty cycles. But you will draw more power for the fan. Any more questions? Yeah.
So in March, I think you also released a PIM4 DD400 gig module.
Uh huh.
See that up there?
Well, that's a hack that we did.
Okay.
Yeah, we were trying to hack this DD 400 gig. Yeah. We built the prototype up.
And we tested it, but we never took it to
Yeah.
production. But
Yeah.
I think the design was actually contributed to OCP.
Mm-hmm.
So anybody can take it, build board, test it, and then roll it out.
What was that called? The name of it? The act?
PIM4DD, that's the project name. Okay, we're out of
Yes,
time.
time's
Thank
up.
you very much.
Thank you very much.